Hey guys, so welcome to another C++ tutorial. In this video, we'll be talking about variables, data types, and memory, which is perhaps one of the easiest and yet one of the like hard to understand and work with topic in C and C++. And I will try my best to demystify things as much as possible from my side, so that you have a clear understanding of how you handle your data in C and C++, because at the end of the day, whenever you're doing some programming, it's just you are working with some data, manipulating some data, and generating some data. So without further delay, let's get started. Let's create a small program, and NVM is just my text editor that I'm using for this demonstration. Let's call it var.cpp. Okay, and this time let's try to get the stdio include right. So include cstdio and int main. So what is data? Data is something that resides in your memory of a computer or any device, and these are nothing but a bunch of zeros and ones like this. Okay, and if you have, let's say, and whenever you are and these are found in basically many places, many chips in your system. One of them are RAM, where all the variables and your codes are also data, are anything that you are interacting with at runtime. That is anything runtime in short. Is and that is a data that is nothing but a sequence of zeros and ones. They reside in your RAM. The same goes for the registers that are in your CPU, obviously. That means your processor chip, and they are the fastest available memory in your system, and they're basically all the variables in action. That means that when you are doing performing the addition, those variables that are being used for addition are there in your RAM, in your register. Then there is also cache, which, as the name suggests, it resides in your CPU. That means your chip, and it acts as a fast storage or for variables uh, that are imported from RAM to be used by the register. So what happens is that you have your variables, they are declared in your RAM, and whenever your program is running, the RAM is much slower than your CPU itself. So what happens is that rather than like going to the RAM again and again to fetch variables and put variables every time, a chunk of variables that are near to each other are taken once at a time, and so that you don't need to like request the RAM again and again and again for different data. The benefit of it is that it improves the performance. We will talk about cache and these other things later. But the idea is that rather than loading one by one variables in your register, we take whatever variable we are taking we need, and also a lot of data that is residing with that particular variable, that is very near to those variables, because there are some philosophies that is called temporal and spatial locality. We call it locality. And what locality means is that whenever you have some variable, the chance is that the next variable that you are going to request is going to be situated very near to it. That is your spatial locality. And the temporal locality suggests that whenever you have a variable, the chance is that you are going to use that variable very soon in the future. Okay, so temporal means times and spatial means space. But at the end of the day, what you need to understand is that your memory is just a contiguous line of data that are zeros and ones. In a 32-bit system, the data is taking 32 bits or zeros and ones at a time, and these are called words. Okay, so rather than like selecting one zero or one particular bit at a time or one particular byte at a time, what your programs typically work on are the words. Okay, that are 32 bits in case of a 32-bit system, which is equivalent to 4 byte, and 64 bits in case of a 64-bit system. In a, let's say, 32-bit system, and 64 bits in a or 8 bytes in a 64-bit system. So typically int, depending on whether you are using a 32-bit system or a 42-bit 64-bit system, it will be either 4 bytes or also like it can also be an 8 bytes on a 64-bit system. And what that means is you can store up to, let's say, 2 to the power 32 number of values inside that memory. How? Let me explain. Let's say I have a 4-bit system. I have 4 bits. Okay. So I can store 0000. Then I can store 0001, and I can store 0010 and so on up to I can go to 1111. Now, how many of these are there? You would ask. The answer is simple. Like every place, it can be either 0 and 1. So you have two possibility for every particular bit. And when you have 32 bits, you have 2 to the power 32 possibilities, because 2 times 2 times 2 up to 32 times. And that's the largest value of integer that you can store, nothing else. And but let's go to that later. So what I want to tell you is that whenever you declare a variable, there is a place in your RAM. Okay, let's say at 3000 position, you have a your variable A residing, and this 3000 is address. And what does the address means? Address means that from the beginning of your data, okay, going by the words, like word length, like every 32 bit in case of 32-bit system, and every 64 bit in a 64-bit system, what is the offset? Like for example, your RAM is something like this in a 4-bit system, 00000000, and so on. So this is going to be your address 0. This is going to be your address 1. This is going to be your address 0. This is going to be your address 1. This is going to be your address 2. This is going to be your address 3, and so on. This is going to be your address 4, 5, 6, and 7, so on. And let's say I request for a variable. Let's say I say int a equals to, let's say, 10, or let's say int a equals to 5. So we have something whenever you say that this, our OS, it has some like memory management system. um, Whether it, so what it does is it says that, okay, let's say for at C place I have sufficient empty space where I can store this value. So what it does is it says that, okay, at 3 place, let's put 5 here. 101 means 4 plus 1, which is equals to 5. So what it does is that it says that, okay, at 3 place store 5 here, And whenever that person who has declared A, whenever A is used, go to that third place, go to the third place and fetch whatever value is there. Okay, so I am putting asterisk here to say that whatever the value is there in the third place, you fetch that value. And this 3 is also known as pointer. Okay. And so we can just simply say that the address of A, also represented as like ampersand A, is equals to 3 here. This is an bare bone example. The system is not going to be 4-bit, it is going to be 32-bit or 64-bit. But that is the idea. Okay, like whenever you need to get the value stored in a particular location, all you need to do is you type that location of your RAM, also known as pointer. Let's say at 3000, whatever, like which means that the 3000 uh, word in your contiguous memory, that is your RAM. And whenever I put like asterisk in front of it, it means that whatever that value is there, just get it, and which is in this case equals to 5. The same can be said that like if this is 3 actually, in if we take the above example, if we say that this variable a give me its like address. So if we say that at n% a, it gives me 3, which is nothing but the address where that variable is stored. So a variable contains one thing, that is what particular address that variable is stored at, and the value itself is stored in the same address in the RAM. So the variable that you declare, they actually contain the address, nothing else. Okay, if that's clear to you. And whenever you declare a pointer, it contains a variable which declares an address. Now it becomes becoming confusing, so we will come to that a bit later. But that's what going on in your system. So as I have said, that int, it can be 32-bit or 64-bit depending on your system. What you can do is you can include a header file which has some like definitions to make things like consistent. It's called stdint, okay, .h or cstdint. And then you can use these two types to like specify whether you want 32-bit or 64-bit by saying in 32 underscore t, that is so surely going to be 4 bytes, and in 64 underscore t, that is surely going to be 8 bytes. And and these in 32, in 64, these are called data types. What data types are used to interpret how the value is supposed to be used. For example, I have a value like this, 00100, like this. Okay, like this is just an example. Okay, so let's say this is 1 2 3 4 5 6 7 8. Yeah. So let's say this is an 8-bit value in an 8-bit system. Yeah. This is like 1 byte, and this is suppose my int a is equals to particular this thing. Okay, although you can't declare it like this, what you can do is you can use 0x to define hexadecimal values. For example, if I say 0x 12, that is equivalent to uh, whatever x represents, that is 0001. Always like one hex code is equivalent to 4 binary codes, so it makes easier for us to declare. And then the 2 is represented by this. So the value of a that is stored in memory is this. Okay. So now in case of using int, it says that okay, treat this memory as an integer. But if I say, let's say that uh, character a, okay, so character a, it means that although this value is this, which is equivalent to 0x12, or whatever its equivalent in decibel. Let's see if the AI can find out to 18. Character A will be like the same 18, represents whatever character it is. Okay. For example, it may represent a space or anything else. I'm not saying that it represents a space, but it might represent a space. Like for example, if I say that int a is equals to 97, for example, it's equivalent to the character a. So how you put the type of the variable, it helps you to distinguish two things. First of all, how like the position I am specifying in the RAM, because only your variable contains the position. From that, how much space I need to consider inside the variable. In case of int, its size is defined there. In case of character, it's only 1 byte of data, so it's 8 bits. In case of, let's say, float, it's 4 byte. In case of double, it's 8 byte, and so on. In case of bool, it's also like 1 byte. Okay, and so on. So first thing first, the data type, these int character, these are data types. The data type says that how much data I need to consider from the location where my variable is stored. And the second thing is that how I want to interpret the data. For example, in case of integers, you can just convert the whatever binary value is present there, and whatever it's in decibel, that is the value that is being considered. But let's say if I'm using a character, it's going to be the character that is that is that represents that particular number. For example, 97 represents a, and so on. Okay. uh, then, like, if you are using, let's say, float. In case of float, the same data, it stores a decimal number. Now you will ask that how it stores a decimal number. Decimal number, that means a number with like number, like such numbers as like 10.3. So you will ask how this 10.3 is going to be stored as this. Okay. So the clever idea that they come with is, in a float, the data is stored into three parts. Okay, it's the first part is your sign bit, which says that whether it's then you have this exponent and you have the mantissa. Okay. And in case of like int also, you have your first, you have the sign bit, followed by whatever the number is. Okay. And like, this is just an example. I don't like absolutely remember whether it's like float contains sign bit, or that just the exponent itself makes the decision, and so on. But you get the idea, like, or the mantissa might be before exponent, and so on. The best guide in this case is internet. You can go to internet and you can see that floating point variable, and in binary, and you will, like, if it's correct. So you can see that there is sign bit, then there is your exponent, and then there is your mantissa. So this is a 64-bit number, I guess. So like 52 bits for mantissa, uh, 11 bits for the exponent, and 1 bit for the sign bit. Now, what sign bit, exponent, and mantissa means, and let me clear it out. So mantissa is the core number. Like for example, 10 is the like for example, let's say 20 is my mantissa, and then my exponent is, let's say, 4. Okay, and my sign bit is either 0 or 1. Okay, so 0 means that this is a positive number. Okay, if the sign bit is 0, it means this is a positive number. So it takes only 1 bit. Okay, so in this is 1 bit, This is 11 bit and this is 52 bit according to a 64-bit variable in this is C or C sharp. I don't know. Yeah, this is in case of C sharp, but it should be like same for C++ also in a 64-bit system. And whereas 1, if the sign bit value is 1, then it means that it is a negative number. That means that whether the number starts with 0 and 1. And the sign bit is also present in case of integer. If you want the purely the number, you don't want to consider any negative number, only positive numbers, then what you can do is you can use something called unsigned int. Okay. It's the same size as int, but the difference is that in case of integer, one bit is used for the sign. Okay. So the value that you can actually use is up to this many slots because one bit is used for sign because you have negative numbers and positive numbers. So it will go from like negative minus 2 to the power 31 to it will go to up to 2 to the power 2 to the power 31. It will go to 2 to the power 31 minus 1 to I think like 2 to the power 31 or something like this because 0 is also there. That to get the idea. Okay. So that is there. And then you can put unsigned there and it will take you from 0 to like you have all the bits here because the like you can use up from 0 to the power 32 here. Actually, 2 to the power 32 and minus 1 because like there are total 2 to the power 32 values which is from 0 to 2 to the power 32 minus 1. There are 2 to the power 32 with two values. Okay, to the power 32 values, right? And an alternative is that like here is int and int 64. You can also say that u int 32 underscore t, which will be equivalent to an unsigned integer of 32 bit, and u int 64 underscore t, which will be equivalent to 8 bit integer, that is an unsigned integer. So you can use any of these. And in case of float, what I was trying to say is that the 0 and 1, they are the sign. The same goes for integer. Then there comes the exponent and the mantissa. The mantissa itself is the number so in this case, like if the mantissa is 20, then it's just 20. And then the exponent means that 2 to the power, the exponent is multiplied with the mantissa, nothing else. Okay. Like it's nothing but whatever the sign bit is, that is the whether it's positive or negative, and after the sign bit, that is nothing but plus minus in this case, and then your mantissa times 2 to the power the exponent. Okay, yeah, that is the like idea behind the floating point numbers. Okay, and that's why there is a common term that is used called precision. And what precision means is that like up to like between two smallest nearby values, between two values that are very nearby to each other, how much difference is there? For example, in case of integer, the smallest difference is 1, right? Like for example, I have 2 and 3. The smallest difference like between two consecutive value, the smallest difference is nothing but 1, right? But in case of a floating point number, I have a limited number of dots I can go. Like for example, I can go up to like 4 places only. So like I can, like for example, I can say 0.2222, and the next value I can say is 0.222, let's say 4. Just for example, I like 2223 or something like that. So in that case, the smallest difference that I can store is 0.0001, and this is the precision of that particular floating point number. Now I'm not saying that this is the precision for floating point number, but you can just calculate it from the like exponent itself. Okay, like put 1 here and take the exponent to the like lowest exponent that is possible, and whatever you get out of it is particularly that. And in case of exponent, you will say that okay, how are you saying that it's going to be divisible? Because the exponent starts from a negative number. Okay, like some the exponent goes from negative value to some positive value, and there is like predefined base value. So, like for example, if my exponent is let's say 7, and my base value that that my system decides is let's say 4, so it will be equivalent to like whatever my mantissa is times 2 to the power that particular base value minus like exponent minus base value, so 7 minus 4. So if my exponent value is just let's say 1, so it will be equivalent to like m times 7 minus like 1 minus 4, which will obviously be 2 to the power minus 3, and you get yourself a fraction. Okay. And the sign bit finally decides whether the fraction is positive or negative. So that's like going behind the scenes for a floating point number. And in case of double, just the storage space for like mantis and the yeah, your bits are increased, nothing else. Okay. And so on. And by the way, doubles are 64-bit floating point numbers. Float are 4-bit floating point numbers. So the mantis and the exponent will be even smaller. So that's how typically things go by. Let's just remove whatever crap we have done here and like get into some actual programming. So what happens is that whenever you are inside a scope, in this case I am in the main scope, whatever you declare, let's say I say int a equals to 10, int b equals to 30, and then let's say character c equals to 4. Then I have some code here, and then I get out of this function. So what happens is that you have your RAM itself is divided into two parts. One is your stack, and another is your heap. Okay. So the difference between stack and heap is that heap is allocated by a heap allocator, and it's provided by your OS. Okay. Keywords such as new, delete in C++, or functions like malloc can help you to allocate memory in your heap. But whenever you declare a variable like this, they are declared inside the stack. And stack is nothing but you can think of it as like stack of things. Okay, stack of things means what? Like you have a biscuit packet of which one side is open. So, like let's say I had some things already inside the biscuit packet, and now I came into this function. In this case, the main function. Whatever was inside the stack, these values are appended. Okay, so 10, 30, and 4 are appended. And obviously, you can just assign 4 to character C. What it will represent is whatever character is represented by the 4 value itself. Okay, so uh, you can interchangeably use. And whenever like you have there are things like typecasting and so on. We will get into those later. But the idea is that whenever you're declaring a variable, those variables are being declared one after another in your stack. Okay. And there is a finite amount of stack after that heap starts. So if your memory is too large, you will not be able to declare your variables all in stack. So you will probably need to use heap. Because in heap, what happens is that let's say some variable 2 is here, then there is a long gap, and then there is some other contiguous data is there, and then there is some other long gap, nobody knows how, and there is some other memory. So as you can see, the value here is actually fragmented. So this is how the heap looks like, and this is how the stack looks like. The benefit of it is that whenever a function is executing, like in this case, this main function is executing, the values are pushed into your stack one after another. And when the execution is done, the values are popped out of the stack. Okay. And there is a special register in your system or your CPU or chip or whatever you want to call it, your processor. It's called stack pointer, which keeps track that okay, this is the top of my stack. Okay. Like when you go to data structures and stuff like that, I will say that this like it says that let's say uh, this is the top of my stack. Okay. So for example, in this particular scenario, 10, 30, and 4 are there. And then let's say you call some function func here. Okay. And inside the declaration of func, let's say you have a void func here. You have some other variables, that is let's say int a equals to 4 and int b equals to 5. So whenever this function is executed, called, though the top of the stack will shift here, and that our stack pointer, that is nothing but your stack pointer, and this is a register that is present in your uh, card itself, your processor card itself, and then 4 and 5 are added. You get the picture. Okay, so it's moved here, let's say, and then the rest of the stack is always empty. And then this function, it 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 it's done executing, and now now you are here. So because this function has already returned, whenever the function returns, the top of the stack is restored. So once again, the top of the stack is restored here, and this is how like typically declared, these kind of declared variables are kept track of, right? Now for the info dump, you can go to internet, you can search for data types, and you can get like all the types of data that is available in the, you should write data types in C++ or C, whatever. And you can go to Geeks for Geeks. It's a good site, but I would prefer that CPP reference is good, because like references contain like all the documentation. So it's a good place to have everything. But you can see that this is the list that you can declare. Like you can sort to have like half, or you can just simply say int 16 underscore t, whatever prefers you. Like if you don't like sort, you can use int 16 underscore t. And like what the values are, like at least how many bytes you are going to have in your variable, it's there. Then there is boolean type, you have bool. Then there is character type, there is character. You can also like say unsigned character, although like if you're using character, most likely you are trying to do something with um, characters. And that's once again what I said you, that whatever is stored is at the end of the day is a number. Okay, so whether you are storing it as an integer, whether you are storing it as a float, it doesn't really make sense. And then there are like all these other types, like basically these are the fundamental types. Then there you have like floating point numbers, you have uh, floating point numbers, and you have doubles, which are like double sized floating point numbers. Okay, somebody really made a joke, so they called doubles. And all of these types you get pointers of them as well. In pointers, as I told you earlier, we will discuss this in a later video, probably the next. But pointers are the type of the, like the locations themselves where the variable is stored. And what a variable is. A variable is nothing but a location in RAM where some value is stored, or you can, and whenever you use that variable, um, whatever value is stored inside that particular location is loaded to your register and is used. Okay. So, and the same goes for pointers. Like pointers are simply declared like this, like say, uh, int a underscore ptr, which is a pointer to a, and I can say that it refers to the same address of where a is stored. Now let's say our a is stored as 3000 position. At 3000 position in our RAM, 10 was stored. So now when I say that int a pointer is equals to a, what happens is that it takes 4 bytes for one integer. So at 3003, after 4 bytes, after 3000, at 3000, 0, in 3001, 2, 3. So at 3004, the value 3000 will be stored. Okay, this is my a and this is my APTR. Okay, and because these variables are declared in stack, so most likely they will be declared one after another. Then at 3008 your B is stored, and then at 3012 your C is stored, and let's say I have and float D, which is like 3.14. So at like 3013, not 3016, but at 3013, because character is 1 byte, your 3.4 is stored. Okay, so this is how this particular declaration is laid out in your memory. Okay, and whenever you say that I want to use this particular uh, variable or like symbol that I have declared, if you use directly, whatever is stored there is loaded to your RAM. So in this case, when I say that a, instead of this 3000, what is stored there, this 10 is loaded, and it also makes sure that only like the next 4 bytes are loaded because a is declared as int. So this is the benefit of the types. Same goes for like aptr. Whenever you are declaring a pointer, let's make it a pointer. So in case of a pointer, what happens is that it's same as an integer. Like all pointers are integer. Like whether you are declaring an integer pointer, if you are declaring a floating point pointer, it does not matter. All pointers are integers because at the end of the day, pointers are just memory locations. So whenever I say that int a ptr is equals to a, say address of a, it says that okay, whatever, whenever you say address of a, this is an address of operator. When you say address of a, it says that where a is stored. Now a is stored at 3000. So 3000 is assigned to the value of the pointer. That is, pointer itself is declared at a separate space in your memory, and it's obviously an like the longest integer that is possible. In case of a 64-bit system, a pointer is 64-bit long. In case of a 32-bit system, a pointer is 32-bit long, and that particular uh, value of that location is another location's address or another location itself. And how you access the pointer? So if you need to get the value that is stored at a, you can dereference it by using asterisk again in front of it. This asterisk is used at the time of declaration to tell that this is a pointer. The next time you want to access it, you just say asterisk aptr equals to 20. So as soon as you do that, because aptr stored 3000 address and you are dereferencing this asterisk aptr as 20, this value, this area will be used, and so this 10 will become 20. Okay, and so on. So like this the basic pointers work. We will look into pointers and like memories in detail. I think that at this point, if I continue with like pointers and things, it will get more confusing, and I would rather prefer that I put pointers and arrays in one video, so make things simple. What I would rather do is I will go through printf once to give you an idea, a list, printf cpp reference, that what literals you can use to particularly refer to a particular print like kind of value. Okay, so for some reason they think that they are, yeah, no, they are good people. So you whenever you are giving, if you printf a variable, the printf only has access to its like its position. It does not have any access to like what kind of value it is, or like where it is stored, and like what the fuck I'm saying. So whenever you are given giving a passing a variable to printf, you use percentile d, percentile c, etc. They just specify that what kind of like data you want that variable to be treated. Okay. For example, percentile C means that okay, whatever is there, just read one byte and from that location and treat it as a character. If it's percentile S, that means that it is a contiguous block of characters. We'll come into that, which is also called string. Percentile D means that it's a number. Same goes for percentile I. Okay, and so on. Like for floating point numbers, you will use percentile F, and these things. When I go into IO, I will like go deep into it and show you different types of printf. But in this video, with what I can show you is how you can take an input. So for that, like printf prints an input, we can take an input by using scanf. So we can say that I have an integer a, and I want to take the value from the user. I can say scanf, and then I can pass what kind of value I want to store. In this case, I want to store an integer, so I will say percentile d. And because I want to store that value in that particular location, rather than providing the like location itself, rather than providing the variable itself in like how we provided in case of printf, in scanf we provide the location of that variable. So we say that okay, I have two values, let's say a and b. Uh, and both are integers, and I want to store them. Okay, so this is the statement, like int a I say and b, and I want to store them. And also let's remove all this junk from here, otherwise it will not compile. But let's say I have int a and b, and I then scan a and b, and then I want to print whatever the like addition of a and b is. So percentile d plus percentile d is equals to, let's say, percentile d, and I pass a, B, and A and B. So this is the program that will take two values from the user and hopefully produce its addition. So we can try to compile this. We can say that cl var dot cpp. CL is the compiler provided by Microsoft. So I can say var dot exe, and I can provide, let's say, 10 and 34, and it will say that 10 plus 34 is equals to 44. So you can my suggestion will be that you keep on experimenting with these things. And now that I have showed you that like scanning member also exists just like printf. You can use scanf, and you can like do stuffs. You can basically take input, you can use your for loops and those things. You can declare your variables, and suddenly you can feel that your potentials are limitless. Okay, so that's it for today. Hope you guys have enjoyed this babbling of mine, and hope this has like at least a little bit clarified like what variables really are, and how they're used. When we go into pointers and array in the next video, it will be more demystified, and it will put the whole picture together. So you will have a better understanding of the whole thing. So that's it. Hope you have enjoyed this session. Thanks.